In the last section, we were considering defects at the atomic scale or impurities within the mean free path of the electron. In this section, we will take a step back and look at classical mixtures or porous materials. Consider first a simple layered mixture of two materials, alpha and beta, where the alpha here is represented as yellow layers and the beta is represented as these red layers. We're going to consider electrical conduction along the length L and cross-sectional area A, so we place blue electrodes at either end and attach a battery between them, which drives an electrical current in the desired direction. So here we have set up a problem where we really only need to consider current flowing in one dimension, and so we can consider each of these slabs as resistors in a one-dimensional problem. Thus we can consider each slab as a resistor connected in series with other resistors. And so we call this problem a series mixture. For resistors in series, we know that the total resistance is simply the sum of each resistor. Thus we have the effective resistance is the sum of the resistance of each slab. We can now group the resistance of all the slabs of the same material together to give a sum of resistances of the alpha slabs and the beta slabs together. Now the resistance of all the alpha slabs together is the sum of all their lengths divided by the cross-sectional area times the resistivity of the alpha material. Similarly, the resistance of the beta material is the sum of all the lengths of the beta slabs divided by the cross-sectional area and the resistivity of the beta material. Next, we realize that the sum of all the lengths of alpha is related to the volume fraction of alpha in our problem. So we can replace the sum of the alpha lengths with the total length times the volume fraction of the alpha phase. Similarly, for the beta phase, with the volume fraction of beta. Then we recognize we have L over A on both and can bring it over to the resistance side, which gives us the effective resistivity of the entire system is simply the volume fraction of the alpha phase times its resistivity and the volume fraction of the beta phase times its resistivity. Thus we can say that the effective resistivity of a series mixture is the weighted average of the individual resistivities of the two materials, where the weighting fraction is the volume fraction of each material. The problem we described in the last slide is a heterogeneous mixture of alpha and beta arranged in slabs such that they are connected electrically in series. One might also consider the possibility where electrodes are placed on the top and bottom of this sample. In this case, each slab is connected electrically in parallel, and so we should use the resistivity rules for resistances connected in parallel. For a random mixture of material, it's often better to consider the mixture as containing a continuous phase, here shown in yellow, and inside a dispersed phase shown in red. In this case, the resistance of the mixture is a combination of the resistance of both the dispersed phase and the continuous phase, but it's neither exactly in series nor in parallel. In this case, we will use what is called an effective medium approach for the resistance of this mixture that considers both the resistivity of the alpha phase, the beta phase, and the volume fraction, but in a way that mathematically is slightly different from either a perfect series or parallel connection. For the mixture of slabs in series, we derived the resistivity mixture rule. Similarly, for a mixture of slabs in parallel, we would derive a conductivity mixture rule, where the effective conductivity is a weighted average of the conductivity of each material, and again, the weighting function is the volume fraction of each material. For cases where the mixture cannot be described as being electrically in parallel or in series, we use an effective medium mixture rule. For example, the mixture rule of Reynolds describes the effective conductivity of a material which contains a continuous phase and a dispersed phase of primarily spherical particles or voids. we need to know the conductivity of the continuous phase, here shown in yellow, and also the conductivity of the dispersed phase in red, and then also the volume fraction of the dispersed phase, chi. For an example, we can use this effective medium mixture rule to describe a porous material. So consider our material has as its dispersed phase simply pores. These pores or voids in a material will have zero conductivity or infinite resistivity. From the mixture rule of Reynolds, one can then show that the effective resistivity of this mixture is simply the resistivity of the continuous material increased by a factor proportional to the volume fraction of the pores or the porosity. We end here with an example of the resistivity of a two-phase alloy. Consider the two-phase region of a eutectic alloy, here this red region, where at a given composition in the two-phase region we would have an alpha material with composition X1 and a beta material with composition X2. If we wanted then to predict or understand the resistivity of this alloy as a function of composition along the full length of this phase diagram, we would consider the resistance in the single phase region to be determined by Nordheim's rule for both the alpha phase as well as the beta phase. However, for the two-phase region in between, where we have a mixture of both alpha and beta phase, we would expect to use a mixture rule to describe the resistivity. We know that all the mixture rules essentially describe a linear change in resistivity for small volume fractions of the dispersed phase at either end and something continuous in between. Here it's simply shown as a straight line.